and that recording is going to be put on our website later, and all the presenters have agreed that the presentations can go on the website as well. So, right, hopefully you're seeing my next slide. Yeah, so brief introduction from me. We'll then get into 3 separate presentations on each of the projects. That'll be about 15 minutes each. And I'm hoping to leave a solid half hour at the end for Q&A. So if you want to submit questions, please do so via the chat box. During the presentation, we're going to have the cameras, audience cameras and microphones muted. I'm not going to go into all the biographies because that would take a while, but if you want to read people's biographies and a brief description of the projects, you'll find it on the place where you signed up for the webinar. Quick shout out to a couple of the upcoming events which we've got going in the Net Zero programme. In June, we're returning to the subject of carbon capture. It's going to be a more technical session than the last one, which was on business models. So this will cover things like well integrity, reservoir and flow assurance. And then in July, we're looking to put on a webinar financing the energy transition. Break in August and more webinars to follow later in the year. So back to tonight's session. Really, we've got, a massive sort of challenge ahead of us for the oil and gas industry. We are one of the bigger emitters of greenhouse gases, and from what I understand, and I'll learn more tonight, a huge proportion of those emissions are associated with the power, gas generators, diesel generators, providing the current power and heat for our oil and gas projects. So electrification of those seems like a good idea in concept, but how do you go about it in detail? So we'll hear from the Central North Sea Electrification project, which is a large integrated project. We'll hear from the Orcadian Microgrid, which is a more modular approach. And we'll hear from Project NEOS, which is really looking at how you integrate the electricity generated by offshore wind farms into an oil and gas facility. The running order will be Arjit, then Joel, then the Project NEOS team. And so I think without further ado, I will stop sharing my screen. And if I can stop sharing and request that Arjit shares his screen and provides us with the first presentation. Over to you, Arjit.
Hey, hi, Barney. Thanks. I'll start sharing my screen now, and let's see. Let me know when you're able to see it as well.
Yeah, seeing your screen. It's in. It's not in presentation mode yet. Yeah, perfect.
Should be in presentation mode now.
Yeah, that's brilliant. Thanks, Arjit.
All right, thanks, Barney. Right. So I'll talk a bit about the Central North Sea Electrification project. As a way of introduction, I'm the stakeholder manager for Central North Sea Electrification joint venture team. And I am from Shell, so I will take us through what this JV is, what's the objective. But just to kick it off, the joint venture is between Shell, Total, BP, and Harbour Energy. So it's a joint venture with 4 energy companies trying to decarbonize some of the assets in Central North Sea, some of the major assets in Central North Sea. And the another thing to share is that I'm a reservoir engineer by background, so it's incredibly fun to be on both sides of the equation. First, I have been in the operations team as well in Shearwater. Now on the other side, trying to electrify the platform. So fun, and then really enthusiastic kind of experience. Moving on. Right. So a little bit of an introduction on what Central North Sea Electrification is. and what's the key steps of the project. So as I was mentioning, Central North Sea Electrification is a collaboration of 4 companies: Harbour, Total, BP, and Shell. And we are looking at about our 5 assets, producing assets in the Central North Sea, to electrify them. So when we say electrify them, what do we really mean? So these assets currently are using fuel gas for generating the power and for their operations. Be it compression, be it let's say drilling the wells, new wells, so on and so forth. All of this is using fuel gas at this point of time. The project is about, can we move away from fuel gas consumption and move into electrification of these assets, and thereby reduce the carbon footprint of the oil and gas assets. The team has been in place since 2019, and I would like to say that at this point, for nearly 1 year, from 2019 to 2020, it was a bit of an informal approach, trying to see what the high level information on what we can do, what we can really change in the in the platform, so on and so forth. It's really in 2021 when this joint venture was established, and then it is also then that we started seriously looking at what are the different concepts that we can work on to electrify the platforms. Which concepts are best, which concepts deliver long-term value for not only the companies and the assets, but also to the wider community. So we are working still. We are approaching concept select in May to July this year timeframe, and the idea is that at the concept select we will choose about 1 to 2 concepts that we want to go forward with into the pre-feed stage, and in the pre-feed stage we'll be maturing them further, so more engineering work on these concepts, at the end of which we would like to then move into feed. So more onto that later. Would like to say here, so what are the 5 assets actually? So a little bit of introduction on which assets are we connecting, what's the main concepts that we are looking, and some information on the timeline. So the assets that we are looking currently, or the assets which are currently partnered into this approach, are a shear water asset. So that's a gas asset. Then we have Gannet. We have ETAP. So shear water and Gannet from Shell, ETAP from BP. We have Elgin Franklin from Total, Judy platform from J-Block from Harbour, and we have no, that's it. So those are the 5 ones. We had 1 more, but it's now out of the scheme, so won't name that. So these are the 5 assets which are currently in the scheme. Overall, by electrifying them, we are looking at an emissions reduction or an abatement of about 8 million tons per annum. 8 million tons in total, about 1 million tons per annum. So significant abatement via this scheme. And to be able to do that, we are looking at a power requirement of about 200 to 250 megawatts, at least to start with. And then you will see here on the bottom right, the demand goes down with time, and that is a function of when some of these assets COP or basically get decommissioned. So as you might have figured already, then the assets, and if I'm looking at the timeline, some of these assets are actually getting decommissioned in 2032, even starting 2032. So the urgency on getting along with it and start delivering something is huge. So pace is critical to delivering this project. And our ambition is, so while our stated objective is we want to electrify or decarbonize these platforms by 2030. That's not our true ambition. Our true ambition is to electrify them by 2027. So on the timeline bit, like I was saying, concept select milestone in Q2 2022, so this year Q2. Then going into feed next year in March to July timeframe. Final investment decision or the sanction in 2024, and ambition of startup by Q4 2027. Now, these assets that I talked about, these are all about 200 kilometers away from the shore, from Aberdeen, let's say, and about water depth of about 100 meters. And I guess there are therefore, so they are not, so therefore with this distance and with the water depth, there are multiple concepts that can be applicable. So it's really at this stage, it's really about how can we choose the best concept which can deliver the long-term value for these platforms. And some of the concepts that we are reviewing and evaluating currently is, so one of them is a direct cable from the shore, let's say here at the shore, onshore Peterhead, to the offshore hub, and then from the offshore hub to the station. So a direct cable from shore supplying the power to the stations is one of the concepts. Another concept, and building upon it, another concept which we are working on with urgency is, having the power cable to the shore, but also integrating the power requirement with the wind farm, offshore wind farm. So effectively, having a wind farm here in this in the offshore area, in this triangle kind of or polygon that I am currently highlighting, and I will touch more upon it about this opportunity later. But effectively integrating a wind farm, an offshore wind farm, with the power supply from shore, so that we can not only enable the wind farm development, but also bring more renewables or green power into the grid. Other concepts are, and as my friends and colleagues will touch upon later, is off-grid solutions, for example, or power islands or microgrids, those solutions, which don't necessarily connect it to the shore at the start, but again serves to decarbonize some of these platforms as well. So these are some of the concepts that we are evaluating currently, and then I'll take us through some of the progress that we have made on these. Right. Moving on to the next slide. Right. So for us at this point of time, power from shore UK with the wind integration opportunity is the reference case. And in very simple terms, what this concept is bringing a cable from an onshore substation to an offshore hub or an offshore substation, and then from the offshore substation relaying cables to different assets, to 5 different assets that we have on our scheme. Now, what's the advantage of such a scheme? The advantage of this scheme is that we get reliable power from the shore, and we, from a safety point, from process safety point of view, also from a reliability point of view, we want reliable power. So we want to make this connection to the shore. So that's one of the advantages. But then not to forget, the integration with the wind is also something which we are working on, and is something which we are evaluating for the concept select. But then, having said that, there are some key value drivers which will define the concepts that we will move ahead with. And those value drivers are: what's the timeline of delivery, what's the abatement that is possible with different concepts, and then ultimately what's the cost to each of these assets for implementing the solution. So with these value drivers, we are currently evaluating these multiple concepts. I'd like to add here that as a part of this concept, we have applied to a grid connection at Peterhead, and we have I think just a week back or a couple of weeks back, we have received an offer for a grid connection at the shore. So we can then effectively, with our current plans, we can connect to the grid on the shore, onshore, and can supply the power from the grid to the assets. Like I said, optimizations are being currently worked. We are still pre-concept select, so lots of work to be done, and then definitely there are some regulatory enablers or barriers at this point of time that needs to be worked on. And I'm talking about from a consenting point of view, from a marine license point of view, so on and so forth. That still needs to be done to be able to make this a reality. So those are still work in progress, and you will hear more about it in the days and months to come. Right. So wind comes again and again, right? And wind is really critical. Integration with the wind is really critical. I'll skip this bit for now because the next slide is talking about that. And then lastly, what I do want to specify here is that once we take the concept, so a little bit on what's the way forward and what's the forward plans for the project. Now we are approaching concept select gate. After the concept select in May to July timeframe this year, we will be engaging with the markets, not only on the base concept of connecting the assets to the grid, but also on wind integration. We will be doing a RFI, a request for information, from the market, and then following it up with more detailed discussions on how we want to go about it. So more on it coming up, and stay tuned for that. So this is my last slide, and I wanted to use this to highlight the wind integration opportunity, and I guess lots of good work going on in this regards, and also lots of support from not only the market, but also from the regulatory bodies and from government as well. So I want to maybe spend a couple minutes on INTOG. What is really INTOG, and how does that help wind, enabling wind infra development, and also enabling the use of that wind to decarbonize the oil and gas sector. So INTOG is, in very layman terms, is a government scheme which encourages and accelerates the wind development further offshore in North Sea, Central North Sea, simply put. So what it does, based on this, so what it does is it offers licensing areas. So these gray shaded areas here, for example. So this is one of the areas which is up for award during at this INTOG, via this INTOG scheme, and so are these. Well, some of these other gray areas are ScotWind, which was part of a previous wind licensing round, but but INTOG is more further away from the from the shore, more closer to the assets where we need the power, and trying to encourage the wind development closer to the assets. So if I break the INTOG into two components, in and TOG, so in is innovation. So it includes award of license to or blocks to the new technologies or methods, floating, for example, floating wind, which can then run a pilot, or TOG. So that's the other bit of INTOG, which is maximizing the role of offshore wind and enable decarbonization of oil and gas. And these are bigger wind farms, which will then help decarbonize the oil and gas. So wind farms which are more than 100 megawatts in size. Now, how this comes in to this in wind integration, especially for CNSe, is that now this announcement of INTOG was done in February this year. Hopefully, it will encourage lots of wind developers to consider and look at these blocks, these license blocks, and to consider applying for their projects via the INTOG scheme. We as representatives of some of these assets, we are looking forward. So while the decision making will lie with the assets themselves, but Central North Sea Electrification project looks forward to liaise and to integrate with the wind development. So it's a win-win for both, for not only for CNSe but also for wind development, because there is a good opportunity to share the costs of the transmission infrastructure. So imagine things like if we don't have a wind development, we will be laying a cable all the way from, let's say, the center of gravity of these platforms here, 200 kilometers away from the shore, to the Peterhead substation, all at the expense of the oil and gas industry. And moreover, this is only short-lived. So when the assets are decommissioned, the infrastructure is useless. Now, if we integrate it with the wind, then not only the costs are shared with the two parties, but then also longer term, because the wind can be there for longer periods, for even 25 to 60 years onwards. So the infrastructure doesn't become useless when the assets are decommissioned. The infrastructure can be used for longer, and that's the intent, to share the costs of the infrastructure, to enable wind development. So by sharing the costs, so it's a win-win for both wind and the oil and gas assets, and to enable faster development. So we are looking forward to that, and we are looking forward to lots of interest and applications from the wind developers. in INTOG. Of course, so a little bit on, so it's not my forte. It's really Crown Estate Scotland who's owning the process. But the applications into INTOG will start in middle of this year with, let's say, exclusivity agreement, or let's say a first pass screening and awarding of exclusivity agreement to the wind developers by the end of this year. Then the second phase will encompass working the wind developers working their concepts in more detail, along with the oil and gas assets. So it will be a mixed joint effort with the oil and gas and the wind working in tandem to develop a concept which is optimized for both, which will then lead to an options agreement at the end of next year, Q3, Q4 next year. So it's a good opportunity. Really looking forward to it. Like I said, some of the key numbers that I mentioned at the start of my presentation. So about 8 million tons of carbon dioxide that can be abated with this, and basically about 1 million tons per annum, which is huge numbers over there. And I guess the size of the opportunity is, somebody was saying to me earlier, I don't know the numbers from the top of my head, but probably 1/10 of Scotland to be planted or something. So the numbers are huge in terms of the alternatives that can around this. So we are looking forward to working on not only delivering this project but to work with the wind and conclude it. So I'll stop here. I've taken too much of the time already, and we'll hand it back to you, Barney, if that's okay.
Yeah, Arjit, that was fantastic. Thank you very much. I particularly enjoyed hearing about how the offshore wind and the oil sector can work together. I think for too long, as an oil and gas industry, we've been sort of focused on our own stuff and not figuring out how we work with other sectors. And if there's some win-win situations there, then that's fantastic. So, Arjit, if you stop sharing your screen, and Joel, I introduced you before, but Joel's going to talk to us about the Orcadian Microgrid. So if you'd like to start sharing your screen, Joel.
Okay, perfect. Can everyone see my screen? Has that come through?
I can see your screen fine, Joel.
Brilliant. Okay, we'll go for it. So, hi, my name is Joel Maisey. I am, I lead the electrical control and instrumentation discipline at Crondall Energy. We're an independent consultancy specialising in offshore energy, so oil and gas renewables. And I've been project manager for this project for Orcadian Energy. So, Orcadian Energy are an operator in the North Sea. And we've been acting as their client engineers, so their engineering team. And today I'm going to talk around the microgrid concept, apologies, that we've come up with as an alternative to sort of a power from shore, to a cable from shore. So as Arjit was saying, so we're looking to have a self-contained generation and distribution system offshore. So this project has been funded by the NSTA, so similar to Project NEOS that you're going to hear in a second, and also Catoni Engineering. Back in November, the NSTA, or the OGA as they were known then, funded concepts to look at alternative ways to electrify the North Sea, and the three companies were fortunate enough to proceed with that. So the Orcadian Microgrid concept, we've delivered it as a consortium. We saw early on that we needed to engage the supply chain really early to help build a credible solution. As Arjit was saying, we need to be delivering emissions reduction as soon as possible. The sooner we deliver that, the more value they provide. And also we have that 2030 target as part of the North Sea transition deal that's part with industry and with government, that we need to reduce emissions by 50%, and that's a big ask. So the consortium is made up of Orcadian Energy as the sort of custodians of the design, ourselves, Crondall Energy, as the client engineers and developing the concept and managing it. We then have NSMP, so North Sea Midstream Partners, who are an infrastructure investor. They've been helping develop the commercial strategy for this. We've then also got Petrofac on board, who've been helping from an EPC perspective, looking at how we actually construct these microgrids and how we then operate and maintain them. And then we have the supply chain themselves. So we have Wärtsilä on board for reciprocating engines, which I'm going to talk about in a second. And we also have Enertechnos, who are a cable technology provider. So the concept itself, what we're looking at here is, as I say, we've got a solution that we've developed, a microgrid that is self-contained. It provides power to either a single facility or multiple facilities, so the design can be scaled up or down as required by the consumers. And our concept is to make it as simple as possible to electrify North Sea facilities or even further afield. We focus on North Sea for now, but the concept's applicable elsewhere. The optimal size we looked at for a wind farm, sorry, I'll start again. So the key part to reduce emissions with electrification is obviously to get our electricity from renewable sources. So the first thing people think about doing is connecting a floating wind farm into a platform. Now, obviously, that's only part of the answer. What you've then got to look at is, okay, I've got to transform that intermittent energy into reliable energy. And so the way we're looking to do that is we're putting this distribution hub in, which you see with this buoy structure that you see in this center here. And we've looked at different solutions. Won't go into too much detail today on those, but I'm happy to talk about those in the questions later. But the purpose of that distribution hub is to take that intermittent wind energy and transform it into reliable energy that we can then provide to the platforms. And we do that by providing gas-fired backup. So that's reciprocating engines that will fired on gas that are providing the power during those low wind scenarios. But we go a little bit further than that as well, and that we also support those reciprocating engines with energy storage, so with a battery system. That's currently the technology that we've selected. And what that does is it minimizes our spinning reserve. As we'll all know, offshore at the minute, we currently have around a plus or minus 20% spinning reserve in our assets to cope with demand going up and down. And we help to minimize that spinning reserve with this battery. So what we're able to create with these different components is a microgrid. So it's an island microgrid. We're able to deliver reliable power to the platform without that connection back to the grid. So without that HVDC link or HVAC link back to shore. So what I'm going to talk about now is just a couple of the components. I'm afraid this is going to be a bit of a rush through, as we've only got sort of 15 minutes. But again, if you've got questions, please just fire them into the chat. So the first thing I want to talk about, we get a lot of questions about, is the reciprocating engines. And I just want to talk around the key reasons we've selected those over a combined cycle gas turbine or a simple cycle gas turbine. So the first thing is they're highly efficient. So with a 31DF engine, so this 31DF engine, we're able to achieve efficiency of 49%. And if you look at the graph on the top right, that's significantly higher than the current offshore engines, which are down around 30%. But above that as well, we have that high efficiency for a wide load factor. And that's really important for intermittent wind energy, where we're getting lots of wind or low wind. And so we're having to change the loading on those generators. So we can achieve that 49% efficiency from 20% load factor up to 100%. And if you look at that graph on the top right, below 40%, combined cycle gas turbines and simple cycle gas turbines, they fall off a cliff, and their efficiency drops right down. And therefore, you're going to be emitting more during those scenarios, and that's very detrimental when you've got renewable energy that is intermittent. The next thing, the reason we've selected reciprocating engines, is their fast startup time. So we're able to start up within 45 seconds. And if you look down in the bottom right-hand graph, that's significantly faster than even aeroderivative engines that we're seeing offshore at the minute. What that means is we can minimize our spinning reserve. So rather than just having engines sat there running, emitting, but not providing power to the grid, we can use energy storage, and we can shrink the size of that energy storage due to those batteries. So that's really helpful with these reciprocating engines. The next part is they're net zero compatible. So Wärtsilä have stated that these engines, these current generations of engines, will be retrofittable for net zero fuels, so ammonia, biomethanol, hydrogen. And the retrofits they're looking at are very simple. When you compare that with the retrofits that are being looked at for simple cycle gas turbines or combined cycle gas turbines, which are a lot more involved, that's really beneficial for achieving the future when we're going to have to go to net zero, so that 2050 goal of having no emissions from these offshore platforms. They're also compact, so they have a similar footprint to an offshore combined cycle gas turbine. However, they are heavier. Now, one of the ways we've combated this is by having a floating distribution hub, which also makes us depth independent. So the weight is less of a concern for us. And finally, they're low maintenance. They're designed from the ground up for plug and play maintenance. So that classic line of replace offshore, repair onshore, minimize the time we're offshore in that hazardous environment, and we'll do it in a nice warm warehouse or workshop to reduce the time we're offshore. And finally, they're digitally enabled, so we can control them remotely and we can enable predictive maintenance. So the reciprocating engine is a really key component of this. I'm just going to talk through how we've grouped our microgrids. So this area is very similar to what you've just seen with Arjit's presentation. What I'm going to propose here is how we see as the optimal grouping of microgrids. That doesn't mean that this will be the actual application of the microgrids. As I say, we can scale it down to a single facility and still receive all those benefits of emissions reduction, or we can actually scale it up to more facilities, and you'll see in this plot. But it's just to give you an idea of what we see as the most optimal solution for the North Sea. So firstly, we see Microgrid A as Shearwater, Culzean, Lomond. Sorry, apologies. I've got a Shearwater, Culzean, Lomond, and Stella down in the bottom right there. And you'll see the microgrid, which is that green dot. We've placed that near the to minimize cable distances, so that we're able to really drive down the capex that's associated with installing cables. We then have Microgrid C, which is for Elgin Franklin. It's for a single facility because it's got a high power demand. We then have Microgrid D, which is for ETAP, Gannet, and Monarb. You'll notice here that Monarb's a 50 hertz facility. Now, what we're looking at with these is we're doing all of the frequency conversion on the distribution hub, so on our microgrid facilities, so that the consumer, Monarb, is going to receive the power at the right frequency and the right voltage for them. So there's no need to perform any conversion on board their facility. So we're trying to minimize the brownfield mods for them. You'll notice here the wind farms just appeared in the INTOG region, which is the hatched area that you see, and that's the yellow dot. We think there's a benefit by consolidating the wind farms into one location. So we reduce the surveys, reduce the installation time, so save on CapEx, but also save on OpEx because we're only going to a single location to perform maintenance. But again, we're flexible on where that wind farm could be. We then have Microgrid D, so we're going north here. We've got Piper, including the Marigold development, Claymore and Scott. And then we have Microgrid F, which is Forties, Alba, Britannia and Avalon. And then finally, we have Microgrid G. And it's interesting with Microgrid G, I just want to sort of make a point here. We're very flexible with where we get our renewable energy from. If there's an existing wind farm out there, and this links to Project NEOS, we're happy to take power from an existing wind farm and transform that into reliable energy for platforms, but also we're happy to work with developments that are planned in the area. So for example, for Microgrid G, we could be using green volt with these facilities. So that's the sort of where we see the microgrids being located, but I just want to sort of talk around how we're actually going to be providing the energy. So what you see on the graph on the bottom right is the energy supplied, where that's coming from for the microgrid. So the dark blue is the energy provided by floating wind. And as you see, that's providing the majority of power. So we're really driving down emissions. And I'll talk about emissions on the next slide. And then you have the light blue band, which is the power which is having to be provided by reciprocating engines. So that's including your spinning reserve and also providing energy when we've got low wind scenarios. The graph on the right shows the loading of our generation installed on board the distribution hub throughout the year. And there's three things I want you to take away from this graph. The first thing is that the backup generation is running at low load, so less than 20%, for about 55 to 63% of the year. So for the majority of the time, we're only needing about 20% of our installed capacity. So what that means is we need to install multiple smaller generators rather than having fewer big generators, so that we're in that higher efficiency range on the load factor of those generators. The second point from that graph is that we're only running at full load, so over 80% for around 10 to 16% of the year. So what that means is we can accept a lower level of sparing than we typically see on facilities currently. So currently it's around, you have 2 out of 3 engines or 3 out of 4. We might be able to accept less, which helps reduce Capex and OpEx. So the bit that's really important with these microgrids is, how much are we reducing emissions by? So what we have here on the right-hand side is the emissions comparison. So the units of the intensity, so it's the kilograms of CO2 equivalent per megawatt hour. And what you can see here is that for a typical offshore simple cycle gas turbine, we're emitting around 700 kilograms per megawatt hour. A microgrid reduces those emissions by around 80%, so we're down at around 150 kilograms per megawatt hour. And that's assuming we have a wind farm sized to around 120% of demand. What that shows us is, in fact, to meet the 2030 target of a 50% reduction in emissions, we can actually scale the wind farm back. So that helps us reduce the initial Capex for installing these microgrids. So to meet the 2030 target of halving emissions for offshore facilities, we actually only need a wind farm size to 35% of the platform demand. And that helps us develop the project slowly and install the wind farm as we require to reduce, as we need to reduce our emissions further. What we also see from this graph on the right-hand side is that we're able to beat the current UK grid. So the current UK grid is around 210 kilograms per megawatt hour. So we're able to achieve a reduction on that. So I just want to walk through a quick cost comparison. I'm conscious of time, so I'm going to whiz through this. But if we look at these 9 platforms down the bottom right, so microgrid A, C, and D, so that's around 250 megawatts of power. Now, if we look at comparing a power from shore solution with a microgrid solution, we're able to reduce costs by around 18%. Now, you'll see that we've taken the wind farm cost outside of that. And if we include the wind farm cost as an upfront Capex, and that's sized to 120% of demand, we increase costs slightly. Now, the reason we've separated that out is there's different ways we can, different strategies for developing a wind farm. We can either have a lease operate contract, we can have a power purchase agreement, or we can purchase power from an existing wind farm. So the real key with these is looking at OpEx, in fact. So if we look at annual operating costs, the microgrid is significantly lower than purchasing power from the UK grid or the current OpEx for an offshore simple cycle gas turbine. And that's all to do with the fact that the majority of energy is coming from floating wind. So if we then look at this over a 10-year lifespan, that's typically what we're seeing for North Sea assets currently. That's probably increased since everything that's going on at the minute. We're able to reduce the TOTEX cost, so Capex plus 10 years of OpEx, by around 26% compared with a power from shore solution for those assets. So that's around a 2 billion saving. And that reduces the abatement cost by around 44% down to around $200 per ton, which is a brilliant saving for the North Sea. And as I say, we can scale this up or down to a single facility or to multiple facilities to still realize these savings. So if we talk around delivery quickly, and I'm really conscious of time, so apologies, I'm overrunning. What we're looking to do is we've selected technology that is mature. So we made sure that we have a solution that is deliverable and in the water and operational by 2027 to meet those targets for 2030 of reducing emissions by 50%. So what are the advantages of the Orcadian Microgrid? Firstly, what we're doing is we're transforming intermittent renewable energy into reliable low emissions energy for offshore facilities. We're minimizing brownfield modifications for those assets by dropping the voltage down to 33 kilovolts. So the voltage that we're the voltage for the power we're transmitting to these platforms is only at 33 kV. We can drop that lower, but that's a conversation with each consumer, because obviously you're going to have to increase your core size, and there's a cost associated with that. It's scalable and easy to deploy. As I say, we can scale it down to a single facility or up to multiple. And we've gone for a solution that's designed once, build many, so we haven't got to redesign every time. It also provides legacy infrastructure. So what these microgrids enable you to do is power future offshore industry. So that could be hydrogen, that could be carbon sequestration, or we could even connect back to the UK grid in the future. But again, we can push that to the future, and it provides a future use for this infrastructure. And in terms of what we're looking to do in terms of next steps, we've issued a report detailing this concept. Goes into a lot of detail, and that's been handed to all of the operators who are participating in the CNS Accelerated Energy Transition Plan Forum. We've had a presentation with operators who are part of that on the 4th of May, and we've prepared a scope of work, a phased scope of work to enable delivery of this system. And we've done that on a staged approach, so operators can help with the decision of FID. We're also currently formalising the consortium agreement with Wärtsilä, Petrofac, NSMP, Orcadian and Crondall, and we're also looking at an INTOG application to support the delivery of wind power. That's the end of my presentation. So thank you very much. If you've got any questions, please fire them into the chat, and I'd be more than happy to answer them later.
Right, thank you very much, Joel. That was another fascinating presentation. Yeah, I particularly liked this idea of putting a consortium together and the flexibility which you were putting forward there as to how you can connect into lots of different types of platform. So thank you very much, Joel. And as Joel says, keep your questions coming in the chat. So next up is Project NEOS. So it's going to be a combination of 3 people, Bridget, Mungo and Amelia are going to present. So I'm going to be, I need to share my screen because let me. Let's see. Hopefully, are you seeing that in the right presentation mode?
Yep.
Perfect. Okay. Well, I think, Bridget, you're kicking off, so over to you.
Hello. Can you hear me okay?
Yeah.
Okay, wonderful. Okay, next slide then, please, Barney. Yeah, so presenting today, there's myself, Mungo from Neptune Energy and Amelia from Goal 7, and we're the partners in Project NEOS. And we aimed to prove that it was technically feasible to connect, say, offshore wind farm to an oil and gas facility. And we focused on projects, in-flight projects or in-operation projects. And yeah, and we believe that we've proved that it was technically feasible, but it is challenging. And but we, you know, we can't forget the fact that offshore wind is now the second lowest cost new build power generation. And when we're neighbours in the North Sea, it would make sense that oil and gas facilities should be able to access that lower cost electricity direct from the generation facility itself. And I think, as was already alluded to in the previous presentation, there is a huge opportunity to decarbonise oil and gas production here. Next slide, please, Barney. Yeah, so as Project NEOS, we really, I don't need to read this line by line, but basically we set out to prove that it's technically possible, but also try and either validate some of the assumptions that we had, or really, you know, really like cancel some of the assumptions we had. So really, you know, debunking any myths from either industry's perspective. And I think we very much achieved that. So as I mentioned, yes, we're the partners that are presenting here today, but we were also supported by Worley, who did a lot of their heavy lifting engineering work for us. And we really, you know, like I said, whilst it was challenging, or whilst it is challenging, we believe that there's nothing that should make us stop. It's technically feasible. We've identified ways to make it better. That's to say, reduce Capex, and to improve the stability as a result of having variable generation connected to a demand. So yeah, we're going to continue working And with that, I'll hand over to Amelia. And next slide, please, Barney.
So I'm going to look at the technical findings and just give you a summary overview of those. So we started with two base concepts, and you'll see those on the left and right. So the first concept involved a direct connection from the end of two wind turbine arrays, and you'll see two cables there which connect the offshore wind farm to the oil and gas installation. And the reason for this concept is that it required minimal modifications to the existing offshore substation, as an example, and also minimises the level of anticipated investment that might be needed to make that connection to the offshore wind farm. It does restrict how many turbines can be used to deliver power, and that does have an impact on the load factor that can be delivered from that concept. That versus the right-hand side concept, which is a dedicated connection, and you'll see this concept looked at two cables which ran from the wind offshore substation through to the oil and gas platform. This would require some modification to the existing offshore substation, more cost if it was a brownfield modification, but is better suited to perhaps a greenfield development or offshore wind farm that's in the early stages of design, where the design hasn't been locked in yet. So the left-hand concept better suited for brownfield modification, the right-hand better suited where there was an opportunity to build it into the design from the beginning. Next slide, please, Barney. So we went through an optioneering exercise as well, which involved defining a low uptime, medium uptime and high uptime cases. And you'll see down the left-hand side the CO2 reduction that's associated with those. We did model this connection based on a single offshore wind facility, but much like Orcadian are saying, this could be connected to anything. It doesn't need to be an offshore, it doesn't need to be a specific offshore platform, and it could be more than one offshore platform. And again, the enabling thing around hydrogen and carbon capture at a later date. So you've got your low, medium and uptime cases there, and the CO2 reductions associated with them. The reason the high uptime is less than the low uptime for CO2 reduction is because you've got a whole load of redundancy built into that concept. So you've retained the electrical GTGs on the platform as an example, and the gas turbines for compression as backup when you don't have wind power, versus the low uptime case, which is full power from the offshore wind farm. Offshore wind farm powers during normal operations, but a consequence of that is during no wind operation, the platform is offline and relying on emergency diesel generation for essential power, versus the high uptime case where you get a full 100% redundancy and the ability to switch across to either GTGs or gas turbines for compression in no wind scenarios. Next slide, please, Barney. As part of this, we did load factor analysis and looked at energy management. So we looked at the amount of power that the wind farm could supply. So that left-hand bar chart that you're seeing there, so the maximum on that bar chart is the wind power supplied, and the white areas are the gaps that you're seeing in low no wind scenarios. That black line along the bottom is the power required for the offshore oil and gas facility. And part of that load factor analysis was to establish how many periods within a 12-month period there was essentially not enough wind to power an offshore oil and gas installation. And over that year, we had roughly 1,000 hours or 45 days of the year where wind power would not be sufficient for an oil and gas platform. And anybody in the oil and gas world will say, that's not acceptable. We need stable production. This means that an offshore wind farm can't supply the wind power needed to power an oil and gas facility in the absence of something like a cable from shore. So we've come to the same conclusions essentially that Orcadian Energy has come to, is that this concept doesn't work without some sort of energy storage into it in some sort of microgrid arrangement. So that would comprise offshore wind power, an energy storage solution, an energy management system which controls the interfaces between the energy storage system, the wind farm, and also the offshore oil and gas platform. Next slide, please, Barney. And I'm going to pass across to Mungo for this one.
Yeah, so as Bridget talked about at the start, the business case can be viable in certain circumstances. Top left there is really the Capex breakdown for the project, dominated by the subsea cable and installation of the subsea cable, which is directly proportional to the distance from the supplier, from the wind farm. On the lower left-hand side, you can see the 4 dimensions, or as Arjit put it at the beginning, the 4 value drivers that we assessed. And what we're effectively trying to do there was vary those value drivers to find the sweet spot for an NPV neutral project or better. So those 4 dimensions are effectively the upfront capex, which you would expect, the OPEX, the carbon price, which is heavily influential, and the remaining life of the installation. So what we discovered was there is a max capex and a max OPEX threshold, and projects that require additional infrastructure or a bridge-linked platform to house the additional equipment, or redundant cable connections greater than 50 kilometers, or have less than 10 years life left, are likely to be unviable. Converting the capex to OPEX in the form of a tariff, or perhaps a structured PPA to reflect the trends in the OPEX can show promising results, and we need to investigate that further. The other significant factors influencing our carbon price and basically the ability to forecast carbon price robustly, as well as obviously the remaining life. And then to finish, what we really saw was higher gas price forecasting and carbon prices, or the opportunity to extend the life for alternative purposes, can really drastically change the dynamics and therefore the economics. Next slide, please, Barney.
So this slide outlines the key learnings that we've made through collaboration. So the key point we made, and we had suspected that this might be the case in the beginning, is that electrification from an offshore wind farm alone cannot provide adequate levels of reliability to sustain E&P operations. So if this is to work, it needs to be in some sort of system where you can fill the gaps, a microgrid arrangement with energy storage as an example. So those microgrid, they could provide immediate material reductions in emissions, but will require investigations into more sophisticated control systems. So you've got variability on both the wind farm side and the oil and gas platform side, in the seconds. So you need quite a sophisticated control system to allow, to maintain the stability around electrical generation and supply to an oil and gas platform and manage that. We've said already that cable costs are significant. As part of this, we did load flow analysis, which did indicate to us, we built the 2 cables in initially because it was from an offshore wind farm and not a stable source of electricity. But that load flow analysis did show that we could probably do away with the second cable. More work's needed, reliability, availability, maintenance, and all of that good stuff to actually confirm that. But it indicates that that's the case. And if that is the case, that second cable is redundant, then it does significantly decrease the capex costs associated with the project. And also finally, I think everybody knows that the existing oil and gas installations where, for example, motor-driven compressors are already installed and pumps, they are much easier to electrify than your assets that are GT-driven compression. And, it was one of the reasons for having that within the space concept, was that the most challenging oil and gas installations to decarbonise are those that are fitted with gas turbines driving gas compression as well, and how do you decarbonise that? And just some of the softer learnings that we've had around this, we've all got an enhanced understanding of brownfield and greenfield modifications, both on the offshore wind farm and the oil and gas side. It's been a truly collaborative exercise with Ørsted, where both with Ørsted and Neptune, where both sides have been presenting back to the teams within each organisation on, oil and gas technology and how that works versus offshore wind farm technology. So that, it really has helped with cross-industry skills development across the wind sector and the oil and gas sector. Next slide, please, Barney.
And the next, so basically, we've decided we only had 3 months to work on this project, so it was a little bit speedy. So there's still quite a lot of work we need to investigate, but we're continuing. So one of them is how, okay, so now we know that it's technically feasible to do this, but how do you really integrate it with an in-flight offshore wind farm project? That's to do with, things like, procurement timelines for equipment, bearing in mind that these are projects with like quite fixed milestones and gates for delivery of certain things, especially according to the current CFD regime. And if we can't come to a decision in time for being able to connect to one of these projects, are the things that we can do to actually future-proof infrastructure, or the small modifications that we can make on the wind farm itself to enable future decarbonisation opportunities. We're also going to look into development PPA structuring. So as Mungo mentioned, on our side, how we structure the PPA in terms of, the cost and the over the number of years, it doesn't really make a difference. But in terms of the business case for viability of the projects, then structuring the terms and the pricing of the PPA really can make a difference. Also, in offshore wind, we're not used to just connecting to one party. We're used to connecting to the grid, and the grid is generally always available for us to export our power to. So, how do we get our heads around as an industry, things like credit risk and what happens, in terms of an off-taker of last resort and things like that. We've also investigated grid backfeed. So whilst we didn't consider power from shore as within the scope of this project, we know that there is a certain amount of house load that's available for our project, and therefore could the backfeed be enough to enable us to at least remove some of the backup generation requirements to maintain stability while we change over between generation sources. Mungo?
Yeah, so from a brownfield modifications perspective, we do need to further investigate the extent, the optimal design and the costs involved. And key to that is really the potential downtime risks resulting from implementing the electrification, and I'll come to that in a minute. The level of electrification achievable or required, short-term versus long-term repurposing, whether we fully electrify or just partially, and that's really talking to Amelia's point around the conversion to electric drive. The base power levels are relatively easy to abate. It's the larger scale turbine-driven equipment that's hard to abate, and obviously presents that brownfield challenge. So I think as an industry, there needs to be further investigation and really look at focusing on developing wider industry understanding, and maybe developing an innovation catalogue of generic solutions for decarbonisation. And part of that would be to look at the end-to-end availability and reliability, to assess that backup generation and the energy storage required to mitigate those areas of intermittency. And that's both from a day-to-day perspective, but inter-hour and intermittent actually, given the variability on the load side as well as the production side. And then from an oil and gas perspective, we really need to think carefully around our existing operating procedures around gas turbine generators, the number of starts and stops of those generators, how they load shed, and then what that means from an uptime perspective and a production efficiency perspective, and really understand that, so that we can change the way we operate slightly to get the best carbon abatement possible. Over to you, Bridget.
Yeah. Oh, yeah. And then, we're really wondering if there are some, funding mechanisms. So obviously we have the CFD on the offshore wind farm side. There's the launch of the hydrogen CFD on just recently from Maisey as well. And so now we're wondering if there is some access to funding or some funding that we could access that would enable us to make decisions on our projects now that would enable transition or repurposing in the future. And rather than just having exposure to risk if a project, from a cost perspective, if a project's not realised, that some of this money could really help to support that transition. Next slide, please, Barney. Yeah, and we didn't really focus on the regulatory side of our project because that's part of some ongoing work by the Government Regulatory Electrification Group. But we do recognise that there are some significant challenges or maybe even opportunities around not that the non-technical points. So one of them is the consenting regime, which we in offshore wind industry, we generally consent our projects under a marine licence, and we're governed by a regulator like Ofgem, and we're working with Crown Estates, and we have very different stakeholders in our consenting regime compared to the what happens underneath the Petroleum Act and the Pipeline Works Authority. And could there be opportunities to either work in one regime or the other that would enable projects to progress? Then we're also, like I said before, we, the clarity on the future of carbon pricing, some of the forecasts that we see are really, very different in terms of what the reality is and how do we get more confidence around carbon pricing, because that will be a key influencing factor on decision making. Mentioned earlier about this anticipatory investment, if there are things that we can do to our projects to future-proof them now and take those decisions now, but we run a very mean ship in a very competitive environment to try and win CFDs, and it's very hard to make investments without some really strong rationale. And also, so therefore, if there was an opportunity to recover anticipatory investment in the situation where a project's not realised, that could help to de-risk some of that decision making around future proofing. We also just need to confirm with the low carbon contracts company that by doing a configuration like this, by sending power in a different direction away from shore, are we still maintaining the integrity of our CFD contract? We've had some verbal discussions, but I think it needs a more solid position. Next slide, please, Barney. And over to you, Mungo.
Yeah, so just to summarise, we've demonstrated the technical feasibility of the concept and understand both from the offshore wind farm perspective, but also an oil and gas perspective, what it would take to integrate the two and really utilise that available renewable power. The economics, do remain challenging, but require stability in both regulatory regime and carbon pricing in the future. And as Bridget said at the top of the presentation, there's nothing that's telling us to stop, so we'll continue to collaborate and to evaluate the opportunities. So thank you for listening.
Thank you.
Thank you very, very much, Bridget, Amelia and Mungo. That was another very, very interesting presentation. Particularly sort of like going back to that theme of collaboration. Yeah, the group you've put together brings wind sector together with the oil and gas sector, and it probably enables you to answer or ask at least questions which you wouldn't do in isolation. Understanding from each sector how their activities impact on the other is probably critical, and that reflects back to some of the stuff Arjit was saying about those win-win situations when offshore wind and oil and gas can collaborate. I would hope that's the way to go in future. So thank you very much all. I suggest all the presenters come back on with their cameras so we can get into the Q&A. and I'll encourage the audience, please carry on sending in your questions. I think we're all there. Fantastic. I guess let's start with the trickiest stuff first, shall we? The economics of it and the costs and so on. We've got a question in from Willem Bloom, who is asking, any idea what the cost for the electrification scheme would be in dollars per tonne of CO2 mitigated? And in that context, how does that cost compete with CCUS and the emission trading scheme carbon price? So that's a question to kick off. And yeah, I'll get two questions in for the price of one. So a question from myself, probably more directed at Mungo. I really like that quadrant you showed, where it showed where you could get an NPV neutral project. And the question around that, which I guess any of the panelists can jump in and answer as well, is sort of what percentage of projects you've looked at meet that threshold of being NPV neutral or at least NPV positive. So 2 questions. I don't know who wants to go first.
So I'll answer the second one first. We've only looked at one particular concept, which included 2 scenarios. So, you know, both of those scenarios are challenged. But as I said, you know, it's those 4 value drivers that really make up that challenge. I think remaining life for me is a key one, given the maturity of the basin. You know, there are younger assets out there, but there are also a lot of older assets, and in their maybe in their mature stage of life. So electrification of those assets in particular will be extremely challenging. You know, as we said, you know, less than 10 years, it's really hard to amortize that cost in a short period of time, because you can't really use conventional oil and gas economics to justify these projects in the conventional sense.
I can probably help with the carbon price question as well, if that's useful. So
go ahead.
Yeah, so with regards to CCS projects, there's a wide range of costs associated with abatement depending on what the emitter type is. So for example, capturing carbon from an energy like a combustion source versus some sort of chemical process where you've got purer forms of CO2, there's a huge price differential in that, and there's been specific business models set up to address that and bridge the gap between carbon price and what it actually costs to abate the carbon from those emission sources. I think on the side for an electrification project, you know, the economics are challenging. And you're probably looking at some sort of business model to support the implementation of electrification projects, whether that's something like the existing CFD schemes, which are already being established for carbon capture, hydrogen and wind is already actively in CFD schemes. I don't know, it's up to the government to decide that, but you know, at the moment some sort of support to help the business case, because it can't be made alone on carbon price is needed today anyway. Whether that's true in the future with you know, gas prices and carbon price probably remains to be seen.
Mm-hmm.
I think the only thing I'd add sort of to it is Mungo sort of already mentioned it really, which is creating legacy infrastructure. You know, if we look at trying to cover the cost of this over the life of the assets, you know, sort of maybe 5-10 years, then it's really challenging. And I think that's something that, you know, especially with ours, we were looking with the microgrid solution, we're looking for something that, you know, you'd got infrastructure you could redeploy. You know, the wind turbines could be sent to another wind farm, or they could be used in their current location and tied back to the grid. You know, I think that's the key, is to, you know, spread that cost and have a future use for any infrastructure you're putting in. About whether, you know, whether we can make it work in terms of the financials, I think we have to make it work. You know, with the North Sea transition deal, there's not really an option So
Yeah,
maybe build up on what. Sorry, Barney, go for it.
No, I was just going to say that's an interesting point, because we're going to get to the point where the alternative is to shut down production.
Exactly. So to build up on what you were saying, Barney, and what Joel shared, when we started the CNSe project, we did look at CCUS also as an option. Can we capture the flue gas? Can we find an aquifer or a depleted gas field? And certainly that was one of the concepts that we looked at as one of the front runners even back in 2019. I guess when we took a deeper look at it, the costs became prohibitive. Capturing the carbon dioxide and then compressing it, then finding drilling new wells, finding a depleted aquifer or a depleted gas field or an aquifer nearby to inject it, and to safely do it while the operations are ongoing on the platforms. I think was a step too far. And when we compared the economics, when we compared the safety, and when we compared the wind integration aspect, I guess it was becoming very clear that, at least in this case, there are many cases where CCUS is probably better, but at least in this case, it was the second option or not less preferred option compared to electrification. I mean, the dollars per ton number is overwhelmingly high, actually. And it's way higher than the UK ETS carbon prices. Having said that, we can make it better by integrating wind, by having some clever financing models, as was Bridget and Mungo was mentioning in their pack. And of course, with wind, there comes CFD, so maybe there are synergies and benefits for both. It will still remain prohibitively high, I suppose, but this is something which we now think about from an STD point of view, which is what you were mentioning, Barney and Joel. That is something we have to do. We have a commitment to decarbonize these platforms, and we have to do it either by electrification or by CCUS or by some other means, but we have to decarbonize them because these emit about 5%, if I'm not wrong, of the overall emissions in UK.
So is there a message then to the government? There's business support needed here fairly urgently. Otherwise, these projects aren't going to go ahead, and oil and gas production will be shut down.
Can I take that question, or do you guys want to go for it?
You go for it, Arjit.
Yeah. Okay. No, I think yes. I think there is a message here, and we have been in engagements with the government, and government is actually helping us. So there is reciprocity on that front. And the message is, while we are working on these projects and schemes, and then lots of innovation coming, around due to this. So, for example, what Project Neo shared, what Joel shared via the Orcadian and Crondall collaboration, very good ideas coming along. But I think there are still lots of hurdles, and some of these hurdles are purely from just to give an example, the consenting of the for example, the marine license consenting, or the consenting of the marine space near the wind farm, for example. So the amount or the timeline of that consenting process is, from what I've heard, I'm not an expert on that, so by all means correct me and add.
It's a long time.
It's a long time. So two years of bird data, then followed up by at least an year of public consultation process, which adds years. And as soon as it starts adding years, then comes the point which Mungo was making. Assets who are close to decommission, who are getting decommissioned in the next 10 years, if they are now waiting for 5 years to get the approvals and the consents, then so then you lose them. So we can't be losing these assets. We want everybody to be involved, and we want everybody to chip in, and we want everybody to go ahead. So I think that's the message. If somehow we can encourage the processes to be streamlined, I think that would be a win-win for everybody as well. Yes, do you want to add to it? Please go ahead.
Okay, let me, because I want to get some more audience questions in. I think this is a clarification question to you, Arjit. The overview map you showed indicated a wind farm area in blue/grey shade to the immediate east on the Norway side. What is the planned or likely activity for this portion? Is it considered to be included in the CNSe electrification project?
No, it's not part of CNSe. It's on the Norway side of the border. If I'm not wrong, I believe it is the Equinor wind farm, which is supposed to be on stream in 2030, 2032 timeframe. So yeah, so it's about 4 to 5 years beyond our own aspirations, our timeline for startup. So yeah, so no, it's not matching our aspirations here.
Okay, thanks. And this one, I guess, is directed to you, Joel, with an autonomous, and this is from Peter Wilby, with an autonomous microgrid, there are higher risks in terms of delivering electrical stability, e.g. low inertia, reliability and protection, no grid support. So how are those risks addressed?
Yes, good question. So we've done some preliminary electrical analysis on this. So we've looked at transient analysis, losing either generation from wind or from the backup generation, and also losing demand or demand coming online. All of those transient loads and losses are going to cause problems, and especially as Peter's pointed out, in a microgrid, you've got less spinning reserve to help with that. So there's a couple of ways that we're managing that. One is that we're providing spinning reserve. So we are curtailing wind in some scenarios so that we do have spinning reserve running, so that we can cope with either fluctuations in the wind or fluctuations in demand. But we're also, obviously on the wind side, you've got to be looking at your forecasting and things like that. But the main way at the current state that we're looking at with this concept is physical spinning reserve through the generators.
Excellent, excellent. So just a little change of tax from technical. So knowledge sharing and collaboration, this is quite a new area, I guess, or certainly new for the UK. There may be first mover advantage if your particular scheme is successful. So how is it working in terms of collaboration and knowledge sharing? And as a supplementary sort of question to that, Norway has electrified their platforms for some years now. Sort of what learnings are we able to extract from what they've done?
So I think I'll take the collaboration one, because our project, as is the other two actually, is a very collaborative approach. I think in the last few years, the collaboration within the oil and gas industry has got better. I think where we were lagging behind was cross-sector, as you talked about early, Barney. And I think that in the last certainly year, that has improved drastically. We need to see that continue more and have that kind of open dialogue so that we can both understand our individual industries better. NEOS and the other presentations you've seen tonight are just some examples of that, where we are seeing kind of cross sector collaboration. So it's to be encouraged, and I think we've come a long way in the last 12 months. As to maybe if I just comment on the Norway side of things as well, I think one key difference with Norway is the regulatory regime and the governmental support, and that's not an excuse, but it is a reason that it's far more attractive in Norway to electrify. I was talking to Barney before this, and we have an asset in Norway which was developed in the early 2000s, and it's partially electrified, powered from shore. It was just a more, how you say, acceptable way to power the installation. And it seems that the Norwegians are ahead of us with respect to their regulatory regime. And you can see that in day-to-day life with their adoption of electric cars, for instance, and the tax incentives that are involved there too. So yeah, I think that's one key difference is the maturity of the regime and the clarity as well.
Anyone else want to come in on the collaboration and knowledge sharing side of things?
Yeah, I can add something there in terms of like incentives as well. So I think probably Norway, I don't know so much, but I know that they had a lot of opportunity with hydropower and perhaps excess compared to their demand for electricity. And we're just starting to face similar in the offshore wind industry now. So more and more we're facing grid constraints. So that's either not just getting a grid connection, but when you get one, you don't get totally necessarily firm capacity, meaning that if there's a constraint on the onshore grid, then you'll be curtailed. Also in the CFD, you know, price volatility in the CFD, it's one thing getting the CFD, but I don't know if everybody knows when power prices are high, we pay back. But then also when power prices are negative, we don't get the CFD. So in either situation, you know, normally without an additional route to market, you would just perhaps curtail production. And when you've got something like, I don't know, I think I heard last week that there's 86 gigawatts of offshore wind, either in operation, in construction or in development. And our demand for electricity in the UK is only 56 gigawatts in winter peak. We've got to do something with that extra power. We can't just keep building. So I think, so on our side, we've got incentives in terms of, you know, trying to mitigate against price volatility. And then obviously on the oil and gas side, there's the NSTD. So these two things are happening at the same time, so we really are both encouraged to work more together as well.
Brilliant answer. Yeah, and I see Sergio Gomez has been asking what are some of the key differences versus Norway, where new and existing platforms are being electrified. I think we've probably covered that one, but thanks for the question. And I see Amelia's had to drop off, unfortunately. We are sort of starting to run out of time. So I think sort of we've covered a bit of technology, delivery. Are there any, you know, actually maybe just in the last couple of minutes, you know, the thing for me to ask is of each of you really, what are you hoping will happen in the next year or so to make, you know, ease the path for offshore electrification? Is there sort of specific technology which you think needs to be advanced? Is it contractual? Is it something from the government? What would you wish for? Bridget, do you want to go first?
I think, you know, we've identified in our projects that there is control systems are going to play a big part of this, integrated control system, cross-sector integrated control systems. That's going to be a big one to solve.
Okay.
Yeah.
Yeah, Joel.
I was just going to say from my side, I think what we're seeing is around for the INTOG licensing process. You know, it's a little bit unclear exactly how that process is going to evolve. There's a process now, but it's unclear whether that's going to be the process going forward. So I'd really like to see some real clarity on what the INTOG process is going to be going forward.
Arjit, Mungo, what's on your wish list for the next year or so?
Maybe if I go first. So I was going to say INTOG, but Joel, you beat me to it. So what I will say is, you know, what I'm also learning now. So it's a learning curve for everybody. What I'm learning now is there is not as much collaboration between different government bodies as we would hope would there, you know, that they would do. So for example, awarding of all these wind blocks, but then not upgrading the grids is one of the pain points that we often come across. So now these wind farms don't have any grid to connect to because there is no capacity in the grid or it is constrained by the critical path. So I guess better cross collaboration between not only us as industry but also within government and then with government and industry is something I would hope for. And if it can then lead to debottlenecking of grid connections in the future, that would really unlock the wind. And then wind is one way of unlocking the decarbonization in my view. So that would be my wish.
Brilliant. Okay, so that just leaves your last wish, Mungo.
I think two really. One on the technology side is really a better understanding of energy storage solutions whether that be battery, whether that be hydrogen. There's some exciting concepts, subsea hydrogen storage and conversion of that energy. And I know that's probably a bit of a stretch on the wish list for a year's time, but that would really help. The other one is really just clarity of consenting regime that I think Bridget talked about in our presentation between the Petroleum Act and the Electrification Act, or Electricity Act, sorry, and just how we consent this together to make it work from a timeline perspective so that the project's successful.
Okay, well, that brings us nicely to 18:30, which is our deadline for finishing. So it just leaves me to thank all our presenters. Amelia has had to drop off. She sends her apologies in the chat there. But thanks to you all. Thanks also to our sponsor, ERCE. Tune back in a month's time, where we'll be doing a carbon capture related webinar. So thanks to all the audience for attending, and see you next time.